Thank you for inviting me over here. I'm an architect. I'm the odd man out probably. Most of you are engineers over here. Thanks to Amit ji that he asked me to be a part of this presentation and speak about steel probably. But I called him a couple of weeks back and I told him that most of the people will be speaking only about steel as a method of construction. So can you give me a leeway and allow me to talk about metal? Which can be used in architecture. So he was very excited. He said, "Why not? You can, explore." So today's presentation, I am having two aspects over here. One is metal, aluminum, as the method of construction, and MS as another option. This is one of the most famous building that the country has. Has anyone seen this building? No, not even a single person. Oh, probably Mr. Monet, sir. Yes, so Mr. Monet is the structural designer for this building. It's completely done in precast. So footings, columns, beams, and slabs, everything is precast. Hollow core plus double T. I learned a lot from him, especially the joinery details. Monet sir took the project because it was all supposed to be precast, and Bhate Raje were the contractors for this building. Now, incidentally, this building is located in the heart of the city. It's in Kothurud. No one knows about this project primarily because all R&D centers that I designed, 95%, 99% of R&D centers are not meant to be known to common man. However, in 2014, when we started designing this building, Mr. Narendra Modi, who came to power, he said that let's look at Make in India. And this is the first of its kind in the entire country, I would say. Rather, one of the only in the world, wherein we have 2,700 people sitting in this building doing research on engines. We have 24 laboratories inside this facility, and there are 52 test cells. Now, these test cells, actually, they fire the engines, they run the engines, and then they do testing for hours together, weeks together. So just to tell you that some of the engines that can be tested over here are 63 liters engine. A 63 liter engine is, our Fortuner car is 3 liter engine, so 63 liters is, you can imagine how big it is. We'll go to the next slide. Just remember this facade because I'm going to speak on this facade only. So it's a 67 acre campus. You can see the left hand side. You can see this area. This is the area that was given to us for doing this tech center. The remaining facility is still a manufacturing block. All buildings around it are residential facilities. So that was one of the reasons why we went for the precast technology rather than site mix design. Next. Okay, I can shift. Yeah. So it's a very it's one of the biggest footprint building in the country. Each floor plate is around 225,000 square feet. The white portion, what you see are the test cells. The offices are all around it. These are the engine assembly areas, and then we have a lot of laboratories. The interesting part of it was, you see it's a very simple geometry. It's a plain rectangle. And it's a very low-rise structure. It's ground plus 3 structure only. So Cummins, they asked us to do evaluation in terms of the facade. It was very difficult because it was a very linear, long building. And we thought that let's look at different possibilities. So you can see 5 different options were presented to them. Option 1, 2, 3, and 5 were all typical design philosophies. However, you look at option 4. Option 4 was the only one which was slightly different, rather very much different. Of all these 5 options, we did a cost-benefit analysis, evaluation of maintenance, constructability, costing, etc. And all the other options were more or less in the range in terms of the costing. However, option 4 was the most, we didn't have the budget also because no one had done that kind of a crazy structure in the past. Unfortunately or fortunately, Cummins liked option 4, primarily because they wanted to showcase this building as a technology building, and they said the building itself should look like a technical or a new age building. So these are our initial level sketches. I'll just explain you. Sorry. So what you see over here is the main building. It's a ground plus 3 structure. It's a very simple building. It has got fenestrations, it has got masonry, and actually if you strip down this facade, it's a simple rectangular building. We wanted to go green. So as you all know that shading devices will reduce the heat load on the building to a great extent. Of course, we didn't go for a certification per se, but this building qualifies to platinum certification. So we thought of doing a secondary skin. What you see over here are the lines that we started drawing. And if you look at it in detail, none of the point on this facade is at the same projection. So every X, Y, and Z coordinate of this facility, of this facade is different. So you can see that this is 0, 0. That means this point actually sits on the building. This point is 1 meter away. This point is 0.5 meters away. This is 1.5 meters away. So it was a very complex form. And yesterday we discussed about softwares that can be incorporated into such kind of complex designs. So we did use a lot of complex softwares to just do a mapping of how this could work. The next stage was renders, because that was only a basic render. We didn't want all glass building. We are known for not having all glass buildings. Of course, you will see some of the buildings which are all glass because of the client's requests or demands. Here we try to use glass and a combination of clay tile. It's all dry cladding. The entire skin actually shades the building. You can also see some of the horizontal bands over here. These horizontal bands are nothing but the vision panels for the people who are sitting inside. They should also look at what's happening outside. There's a quite wooded area, so a lot of greens are also happening over there. So all elevations were neatly drawn, collectively drawn. You can see the DG set stacks also coming up, and also the exhausts for the test cells. And that was the final render that we showed the clients. The next question was how to build this. So we always believe in mock-ups. So we shortlisted 5 or 6 glazing contractors who could come over here and do the mock-up. So everyone came and they did mock-up, and everyone thought that let's do it in MS. So the substructure, what you see over here, was all in MS. And then there were spider fittings. And then they did welding over here. A lot of my engineering friends will say that this is the worst welding that they have ever seen, and we also felt the same thing. Incidentally, people think that buildings should look nice from outside, but actually buildings should look very nice from inside, because people who are going to sit inside this facility are going to be there for 1/3 of their life. We are going to just pass by the building and we'll just say, wow, this is good or this is bad. So what's going to happen was people who are going to sit on this side of the structure were the people who are going to use this building, and they would always have seen this very awkward looking joint. At some locations, there were 7 or 8 arrays coming and meeting over here, and you can see the workmanship. It was pathetic. None of the glasses were joining each other, and we had a harrowing experience. So we thought, let's look at material apart from MS. So this is what I was mentioning you, that when a person sits inside, the vision what he sees outside is also very critical. So we drew a lot of angles and views from people who are going to sit over here and what they are going to actually see. The orange and the green hatches that you see are the zones where the workstations were going to happen, and there were full height glass. So we also positioned the glazing, which was in line with the people who are going to sit over there. So all the more reason for us to ensure that the facade looks neat and clean from inside as well. So we went searching for good contractor who could give a solution which was very specific to our need. And we found one contractor who's called as VS1. They are from US. They came up with a solution. What you see over here are aluminum profiles. These are extrusions. They are 350 deep and almost 75 to 100 wide. And they actually come from an extrusion agency from China who do extrusions for Boeing and Boeing and other aircrafts. So precision level was extremely good. Second thing was the secondary skin, what you see over here, the primary and the secondary skin, there was going to be a gap in between because we wanted to have the Venturi effect. That means hot air should rise and cold air should come from the bottom. We didn't want these joints to be sealed. So this structure was going to breathe. And when, when water comes in contact with MS or it starts corroding, we didn't want any maintenance to happen in this building. So aluminum was the preferred choice for us in terms of the product. And you see, we haven't done any welding. These are all riveted joints, nut bolted and fixed in position. The only point was these verticals were supposed to be at 1.5 meters center to center. There were almost 1,500 sections that we did for this project because at every 1.5 meters, the profile was changing. That's the engineering drawing. So you can see these are the glasses. These are the DGUs. This is that aluminum profile that I mentioned about, which is a hollow core. This is hollow core, this is all solid. And this is a assembly which actually fixes the glass onto this aluminum framework. And it has got an ability to rotate. So any angle, so when you saw the facade, it was at different planes and different XYZ coordinates. We could actually rotate this particular joinery and it could swivel. This was work in construction. Not even a few millimeters of the site, everything was coordinated, shop drawings were prepared and then executed at the site. You can see even the stays what happened over here are all in aluminum. And then we had checkered plates. Now this is the one, this is a photograph of the completed project. Extremely neat, clean and very geometric in its form. You can also see the joinery detail over here. Actually speaking, you can dismantle this entire structure and you can shift it to any other place without even loss of one single member. The replacement of glass is also very simple. We have these keys over here. They can be opened with an Allen key, and if the glass breaks, we just take the dimension and again fix it back. That's how the building looks now. And you can see the joinery over here. These are all breathing joints. No sealant work. This facade has won the distinction of the largest crazy facade in the entire world. And then we use a similar philosophy for the skylight. Since it was a big footprint of 2 lakh square feet, we actually punctured the building into atriums and allowed the natural light to come in. And the same vertical member, the metal member, we also introduced it in the horizontal manner and put the glass on top of it. That's how it looks from inside. It's a light well. This happens at 4 different locations. Now let's come to the roof. The 4th floor was a dining facility for almost 1,200 people. So you can see the dining happening on all these quadrants. And the central court was an open to sky court. We're not going to have any roof over there. The court was actually going to be a breakout area for all the people who are going to dine over here. Later on, Cummins said that we would like to use this square also. It's quite big, 30 meters by 30 meters. We had already told the structural consultant to factor some kind of a light load over here. So clients were from United States. It's a very cold climatic country where they are from, Columbus. So they said we will use glass. So they were hell-bent on using glass. We were saying no, it's a tropical country. It will get very hot. So they said that we will use the best glass. We'll use double glazing, triple glazing. We'll use coatings and try to reduce the heat load, but nothing will work. But we, just to tell them that, okay, fine, we have worked, we did a simulation. So this is a hyperbolic paraboloid with glass and cable tension wires. This is how it was supposed to look. But then we said that this is not going to work in the Indian climatic condition. We should go for a truss and something which is more to the context of the local climatic conditions. So we had a 30-meter span over here, and we wanted to have a very lightweight structure over here. So we introduced 4 trusses, 1, 2, 3, and then there is another one over here. These are MS tubes which are bent to profile. Again, they are fabricated in 3 different sections, and then they were brought at the side, lifted through a crane and assembled at the 4th level. This diameter is not more than 200 mm, and these verticals that you see are just 125 mm. And then these are the purlins, and then we used multi-wall polycarbonate sheet. It's a 8-layer Danpolon sheet over here, which reduces the heat load to a great extent. And almost 550 people sit in this facility. With the air conditioning ducts. Yeah, thanks.